In 1973, the mathematician Victor Klee proposed a new geometric puzzle which basically consisted in answering how few guards would be sufficient to ensure that an art gallery be fully guarded. Assuming that the guard's field of view covers 360 degrees as well as an unbounded distance. 2 years later, the mathematician Chvátal provided a solution to this problem, and the focus shifted to determining the minimum number of guards required to fully guard an art gallery. A problem that is known today as the art gallery problem. Classically, a guard can be placed at any arbitrary position within the art gallery, but there exists also variants of the problem that restrict the guard placements to only its walls or corners. Respectively, the guards are referred to as point guards, edge guards, or vertex guards. Mathematically, an art gallery is modeled as a simple polygon defined by a finite sequence of distinct vertices, which may also contain inaccessible regions inside it that block the view of a guard and are referred to as holes. The main goal of this video is now to find the minimal number of guards needed to fully guard such an art gallery. So welcome to this video about solving the art gallery problem. Formally, a simple polygon is defined by a sequence of vertices v1, v2 to vn such that the straight line segments between consecutive vertices do not intersect, preventing any overlaps like this. A simple polygon is now simply the connected region bounded by these vertices and edges. Furthermore, one may also place a simple polygon inside another simple polygon. In this case, one refers to it as a simple polygon with holes, which are regions that are inaccessible to the guards, such as walls or pillars. Note that in contrast to what the name suggests, simple polygons can have a quite complicated form, and even many well-known shapes such as a triangle, a square, a pentagon, etc. all fall under this definition. The polygons shown in the animation are all convex, meaning that any line segment between two interior points lies entirely inside the polygon. And if this property does not hold, then the polygon is called concave. And if we even allow overlapping edges, then we are dealing with a complex polygon. For our purposes, it's crucial to distinguish between different types of vertices of a polygon, such as convex and reflex ones. A convex vertex has an internal angle less than 180 degrees, it points outward. And a reflex vertex is one where the internal angle is greater than 180 degrees, it creates an inward dent in the polygon. Other important kinds of vertices are, for instance, ears and mouths. An ear refers to a vertex for which the connecting segment between its consecutive neighbors lies entirely inside the polygon. A mouth, on the other hand, is a vertex for which that diagonal lies entirely outside the polygon, creating a concave indentation. And be aware that not every vertex of a polygon is necessarily an ear or a mouth. In fact, it is easy to construct a polygon such that the diagonal between a vertex's two consecutive neighbors lies neither entirely inside nor entirely outside the polygon. Before we start, we need to define some specific rules, or let it be assumptions, about the guards inside the polygon. First of all, a guard covers a 360-degree field of view, as well as an unbounded distance. And even though guard is the standard term in the literature, I think it makes more intuitive sense to think of the guard as a light bulb. One that shines in all directions for an unbounded distance and whose light can only be blocked by the walls of the art gallery. The goal is then to illuminate the entire polygon by the light bulbs, or equivalently to ensure the surveillance of the entire polygon by the guards. Furthermore, note that the guard can be placed at any position G in the polygon and that he can observe any point P if the line segment from G to P lies entirely within the polygon. In other words, the line segment from G to P is not allowed to exit or to cross the boundary of the polygon. It must be fully contained inside of it. Therefore, a natural question here is, how do we check whether a whole line segment is actually contained in a polygon? Well, we can simply take a certain number of points distributed with a fixed step size that lie on the line segment from G to P. If we take a small step size and all those points lie inside the polygon, then the entire line segment is very likely also contained in the polygon. Otherwise, it's not. So ultimately, we only need to find an argument for why a single point lies inside or outside the polygon. And this leads to the so-called raycasting algorithm, which is based on the following idea. To check whether a certain point, for instance this one, lies inside the polygon, one shoots a ray in an arbitrary direction and counts how many polygon edges it crosses. If the number of crossed edges is odd, then the point lies inside the polygon. Otherwise, if the number of crossed edges is even, it lies outside. And that's basically it. So now we know how to compute all visible points P for a guard placed at a position G in a polygon. The union of all such visible points P defines the so-called visibility polygon of G, here denoted by vis of G. Yes, this is indeed a polygon. In fact, this is even a star-shaped set, and it will play a very important role in this video. From now on, the video is divided into two parts. In the first part, we will answer the question of how many guards are always sufficient to fully guard an art gallery, assuming the art gallery can be represented as a simple polygon without holes. And in the second part, we will then consider how to actually find the minimal number of guards for any specific polygon using optimization techniques. And this will even work for polygons with holes. Note that I restrict myself to polygons without holes in the first part, as this will make things much easier while still including important theorems in this context. So how many guards are always sufficient to guard a simple polygon? Well, the simplest way to ensure the surveillance of an entire polygon is by placing guards at each of its vertices. Therefore, assuming a polygon has n many vertices, one can ensure its surveillance by using n many guards. This may be true, but also very unnecessary, and in practice very expensive if you regard that every single guard must be paid. You really don't want to place a guard at every corner in your art gallery. So what are better choices? To find a lower bound for the number of guards, we have to consider the triangulation of a simple polygon. Triangulation refers simply to drawing of non-intersecting diagonals inside the polygon until it is fully divided into triangles. More specifically, there exists a famous theorem, the Triangulation theorem, which states that any simple polygon with n vertices can be triangulated using exactly n-2 triangles. Since a triangle is a convex polygon, you can place one guard inside each triangle. Then every triangle is under surveillance of at least one guard, and in total we only need n-2 many guards, which is already less than placing n many guards. But this is not the reason why we need this theorem. We will need it later for a very elegant proof. A proof of the triangulation theorem is very simple and based on strong induction over n, the number of vertices of the polygon, with n being greater or equal to 3. In the base case, we consider a simple polygon with n equal to 3 many vertices. In other words, a triangle. This is obviously already triangulated and consists of exactly one triangle, which is indeed equal to n-2. In the induction hypothesis, we assume now that any simple polygon with m vertices can be triangulated using m-2 triangles, for all m between 3 and n-1. For the induction step, we have to take a simple polygon with n vertices and have to show that it can be triangulated using n-2 triangles by applying the induction hypothesis. To show this, let v be the leftmost vertex of the polygon with neighbors u and w. Note that such a leftmost vertex always exists since the polygon is finite. Now there are two cases we have to distinguish. The first one is that the line segment from u to w is a diagonal, meaning that it lies entirely inside the polygon. In this case, we can simply split the polygon along that line to obtain two polygons with fewer than n vertices. The left polygon is already triangulated using one triangle, while the right polygon contains one vertex less than the original, that is n-1 many vertices. By the induction hypothesis, it can therefore be triangulated using n-3 triangles. Hence, gluing the two polygons back together yields a triangulation of the original polygon into n-2 triangles. Now what is in the second case? In the second case, the line segment UW will not be a diagonal, so the situation might look somehow like this. But in that case, there must be a vertex x inside the triangle UVW such that the line from V to x is a diagonal. Similar to before, we can split then the polygon along the line segment, in this case Vx, and obtain two polygons with fewer than n vertices, which can be triangulated respectively using the induction hypothesis. Note that if we assume that one of the two resulting polygons has k many vertices, then the other one must have n-k plus 2 many vertices, since the split is made along the line segment Vx and both polygons share basically the two vertices V and x. By the induction hypothesis, we can triangulate now the bottom polygon using k minus 2 many triangles and the other one using n-k many triangles. Hence we obtain a triangulation of the whole polygon into n-2 many triangles. The previous proof is constructive in the sense that it actually contains the idea of how to triangulate a simple polygon. Together with the so-called two-ears theorem, which states that every simple polygon with more than 3 vertices has at least 2 ears, it follows that any simple polygon with more than 3 vertices must contain an ear that can be clipped off. Therefore, the idea behind the famous triangulation algorithm is to simply iterate over all ears of the polygon and draw a line between their neighboring vertices. Once a line between two neighboring vertices of an ear has been drawn, the ear is no longer considered a part of the polygon in the algorithm. It has basically been clipped off from the polygon. This is also what gives the algorithm its name, the ear clipping algorithm. Probably the most famous theorem in the context of the art gallery problem is Chvátal's art gallery theorem. This theorem states that n divided by 3 rounded down many guards are sometimes necessary and always sufficient to guard a simple polygon with n vertices. Besides Chvátal, the theorem was also proven by Steve Fisk, who provided a remarkably elegant proof using graph coloring, which we will consider now. The proof consists of 4 steps. In the first step, we compute a triangulation of the given simple polygon, which exists by the triangulation theorem. In the second step, we free-color the graph obtained through the triangulation. To do this, we use its weak dual graph. This is an undirected graph in which each vertex represents a triangle and edges connect triangles that share an edge. This graph forms a tree as the polygon has no holes, and a depth-first search starting from a leaf provides a valid order to process the triangles. Basically, you simply select any 3 colors you like and color the triangle at the leaf where the DFS starts in any arbitrary way. For each subsequent triangle visited during DFS, you then assign colors so that there is no conflict with its previously processed adjacent triangle. In the third step, we place now the guards. To do this, we observe first that placing guards at vertices of the same color yields a guarding of the entire polygon, as any guard placed at a vertex can see all triangles that share that vertex. Moreover, placing guards at the vertices assigned with the least frequently used color results in a guard set of at most n divided by 3 rounded down many guards, which guarantees surveillance of the entire polygon. Why exactly n divided by 3? Well, because we have colored n many nodes with 3 different colors in such a way that no 2 adjacent nodes share the same color. In the last step we have to show that n divided by 3 rounded down many guards are sometimes actually necessary to guard a simple polygon. There is basically one class of polygons for which you will need that many guards, and they look like this. This polygon consists of 9 vertices and has 3 spikes. These are constructed in such a way that you actually need as many guards as there are spikes to fully guard the polygon. Moreover, n over 3 many guards are not only sufficient but also necessary for polygons like this. But note here that n over 3 many guards are usually much more than actually needed to guard a simple polygon. For example, for a convex polygon, even a single guard is enough, you don't need n over 3. Note that with the proof of this theorem, we obtain a very beautiful algorithm that combines computational geometry and graph theory, and which can be applied to any simple polygon. Here, for instance, the algorithm applied to a simple polygon with 76 vertices. At the end we obtain a guarding of this polygon using 23 guards, even though much fewer guards are actually needed. And even though approximately n over 3 many guards might not sound like a lot for small polygons, things get much worse for polygons with a large number of vertices. Altogether, Chvátal's art gallery theorem provides a nice theoretical result, but to really get something usable for a real art gallery, we need to dive into the world of optimization. The art gallery problem is closely related to a famous problem from discrete optimization, the so-called set cover problem. In the set cover problem, we are given a finite set of elements called the universe, usually denoted by calligraphic U. Additionally, we are given a family of subsets of this universe denoted by calligraphic S. We are now specifically interested in finding subsets calligraphic C of calligraphic S such that the union of all sets in calligraphic C equals calligraphic U. Such a selection of sets is called a cover of calligraphic U. More precisely, the set cover problem asks now for such a cover of the universe with minimum cardinality. So in summary, the motto here is pick as few sets as possible while still covering the entire universe. For illustrative purposes, let us assume here that our universe consists, for instance, of the numbers from 1 to 5. You can think of the universe as a collection of items needed for some recipe. Now, for some reason you cannot buy the ingredients separately, but only in predefined packages labeled as S1, S2, S3, S4 and S5. The set of all these available packages is denoted by calligraphic S. The goal is now to buy as few packages as possible to still cover all ingredients. Specifically, we are searching here for a cover of the universe with minimum size. Now, what are covers in this example? If you look closely, you see that the set containing S1 and S2, for instance, does not form a cover, since the union of S1 and S2 forms the set containing the elements 1, 2 and 5, which does not equal calligraphic U because the elements 3 and 4, so the mushrooms and the sweet potatoes, are missing. On the other hand, the set containing S1, S3 and S4 does form a cover of calligraphic U, since the union of S1, S3 and S4 is the entire universe. However, this cover is not of minimal size as it contains 3 sets. In fact, there is also a smaller cover of calligraphic U containing only the sets S2 and S3. And this is exactly what the set cover problem is asking for, a cover of the universe with minimal size. To solve the set cover problem in practice, one usually formulates it as an integer linear program, also called an ILP. An ILP is a minimization problem with a linear objective function, linear constraints which together form a polyhedron, and the restriction that the variables must take integer values. In summary, the goal here is to find the integer point in the polyhedron for which the objective linear function is minimal. Specifically in the case of the set cover problem, we have the additional restriction that not all integer points are allowed, but only those whose components attain the values 0 or 1. Regarding this, we introduce a variable for each set Si in calligraphic S, denoted by xSi, which can only be 0 or 1. The idea is that if the binary variable xSi is equal to 1, then the set Si is included in the cover, and if it is equal to 0, then it is not. The objective to minimize is then simply the sum over all these binary variables, as we want to select as few sets as possible. Furthermore, we also need constraints that ensure that our solution actually covers every element in the universe. These constraints look like this. They ensure that for every element U in calligraphic U, the sum over all variables whose corresponding sets contain U must be at least 1. In other words, for any given element U from the universe, at least one of the selected sets must contain U. This is an expression of the set cover problem using integer linear programming, but it is rather a mathematical, or let's say a theoretical expression of the problem. What I want to say is that we need to modify it slightly to solve it using an ILP solver on a computer. Since we are minimizing here the sum over all binary variables, we can replace the objective by the sum from I equal to 1 up to the cardinality of calligraphic S over xi, with xi being equal to 0 or 1. Very important is now to rewrite the inequality constraints into a usable form for a solver. Something like a matrix times the variable vector x being component-wise greater than or equal to a vector. This is generally done by defining a binary matrix A with as many rows as there are elements in the universe, and as many columns as there are sets in calligraphic S. The entry in row I and column j of this matrix is then equal to 1 if Sj contains the element ui and 0 otherwise. Now when you see this for the first time, it may look a bit overwhelming, so let us transform our example above into this form to let that sink in. Trust me, it's much easier than it looks like. First, we notice that there are 5 sets available, which is where we have 5 binary variables reaching from x1 up to x5. The main work lies now basically in the construction of the matrix A. Remember that this matrix has a row for every element from the universe and a column for every available set. In column 1 we insert a 1 into every row for which the corresponding element is contained in the set S1. Since S1 contains only the elements 1 and 2, that is U1 and U2, we insert a 1 into the first 2 rows and the rest remain 0 in this column. In the next column we insert a 1 into those rows whose elements are contained in S2, that is row 1, 2 and 5. And similarly we proceed with the other columns. This matrix has to be multiplied now with our variable vector x, and the result has to be component-wise greater than or equal to 1, because then all elements from the universe are covered. So we have a row for every element of the universe, and if the component xi is equal to 1, then we add the set Si to our cover, and thus we cover all elements where the column of Si contains a 1. As this is very important for the whole video, let me point out the most important things once again. First, note that all variables from x1 up to x5 can only be 0 or 1, not any other number. Note also that feasible for this optimization problem are only those values of x1 to x5 that satisfy the system of inequalities. A feasible solution would be, for instance, the point 1, 0, 1, 1, 0, as the sum of the columns 1, 3 and 4 is component-wise greater than or equal to 1. The solution of this optimization problem selects among all feasible points the one for which the sum is minimal. Hence it selects as few sets as possible to cover the underlying universe. Well, obviously only if there's a solution. Problems like this are very popular in optimization, and there is an enormous amount of theory behind solving such problems. But for this video this is unimportant. What matters is only how to obtain a solution using your PC. And this is actually surprisingly easy. You can use, for instance, the Python library cvxpy. Here you define your matrix, your variables, the objective to minimize, as well as the constraints, and then you basically just hit solve. And don't panic if it takes a long time for your PC to find a solution, or if it doesn't even manage to generate a solution for big problems. This is generally unavoidable, as the problem itself is a kind of complex problem. In the next chapter we will consider the relation between the set cover problem and the art gallery problem. Now let us consider first the case of vertex guards, meaning the art gallery problem with the restriction that possible guards can only be placed at the vertices of the polygon. Note that the guard placed at each vertex would be able to observe a certain region of the polygon, represented by its visibility polygon. Here one can come up with the idea of plotting the visibility polygon for each possible guard position simultaneously. Furthermore, let us label the guards from G1 up to G12, and let us define the set of all possible guard positions as G. The overlapping visibility polygons, specifically the overlapping edges, define the arrangement of the guard set G, denoted by R of G. Such an arrangement can obviously be created for any polygon with a finite set of possible guard positions G. This geometric arrangement divides our polygon into disjoint polygonal faces, here labeled from F1 up to F17. These faces define the so-called atomic visibility polygons, AVPs, of the arrangement of G. And although that's a common term in the literature, I will just call them faces here to make things simpler. Maybe you see now the connection to the set cover problem. Remember that our goal is to cover the entire polygon, and the entire polygon consists now of many polygonal faces. Hence our universe is obviously the set of all these faces. The set S1 is then the set containing all faces visible from guard number 1. In this case these are F1, F2, F3, F4 and F5. Similarly, S2 consists of the faces visible from guard 2. By doing this for all possible guard positions, we obtain a collection of available sets, which together define calligraphic S. And now we have a set cover problem as we've seen previously, and we can model it as an integer linear program. First we need the big matrix with as many rows as there are elements in the universe and as many columns as there are sets. Our variable vector is obviously 12-dimensional, since we have 12 sets to choose from, and thus the whole model reads like this. This model can be solved in Python as shown previously, and the solution gives the minimal number of guards from the fixed guard positions at the vertices that are needed to fully cover the polygon. Now when we consider the previous arrangement once again, we see that there's actually no real restriction requiring the possible guard positions to be placed at the vertices. We can take here any finite number of possible guard positions, compute the arrangement and solve the resulting set cover problem. Therefore, an immediate question might be, why not simply choose as many guard positions as we want, make the set G as large as possible, and then solve the resulting set cover problem? Wouldn't that guarantee that we find the solution very close to the true minimum? Well, there are two major reasons why this is not so straightforward. First of all, the arrangement can become very complicated with many guard positions, leading to an obscene number of faces inside the polygon, which can even cause numerical problems as some faces may become extremely small. Furthermore, an extremely large set of possible guard positions makes the resulting optimization problem much harder to solve, since there will be way too many variables in the ILP. And what I haven't told you yet is that the set cover problem, or more specifically its decision variant, is an NP-complete problem. This means that it belongs to a class of problems that can be verified quickly but are in general very slow to solve, which is the reason why there will always be instances that make your PC burn. Altogether, things are not looking so good, as the art gallery problem with finitely many fixed guard positions is basically a set cover problem, which is already hard to solve when the number of guards becomes very large. Even worse is that the real art gallery problem is even more complicated, because you have to find the best set of guard positions among all possible infinitely many positions inside the polygon. This is now a typical situation where mathematicians come into play. They analyze the problem and search for clever methods to obtain reasonably good solutions in practice that don't take an eternity to compute. What I want to show you in this part of the video is essentially the foundation for probably one of the best algorithms in the context of the art gallery problem. Namely, a part of the algorithm presented in the paper, a practical iterative algorithm for the art gallery problem using integer linear programming by Tosoni et al. The algorithm is actually surprisingly easy and is mainly based on iteratively solving cleverly modeled set cover instances. The art gallery problem can be formulated as an integer linear program, but one which is practically unsolvable. The idea is simple: introduce a binary variable for every single point in the polygon and minimize then the sum over all those variables, and yes, this is an infinite sum. The inequalities are then that for each point P in the polygon, the sum over all binary variables of the guards that can see P must be greater than or equal to 1. This looks extremely similar to the set cover problem. In fact, the only difference lies in the existence of infinitely many variables and infinitely many inequalities. To tackle these infinitely many inequalities, we introduce a finite subset W of the polygon P and replace the coverage constraints for all points in the polygon with coverage constraints for all the points in W. The points in W are so-called witnesses, or witness points. This optimization problem, which focuses only on the surveillance of the witness points from W, gets the name AGPW in this video. Please remember that the solution of the AGPW problem computes the smallest possible set of guards among all possible guard placements in the whole polygon that covers the points in W. Regarding this, a solution of the AGPW problem will always contain fewer or equally many guards as a solution for the real art gallery problem, since you aim to cover fewer points in the polygon. Now, of course, there are still infinitely many variables in this optimization problem, but interestingly, we will be able to argue while only certain finitely many possible guard positions needs to be considered here. Of course, one should generally place the finitely many witness points in such a way that the solution of AGPW covers the entire polygon. But of course there is no recipe for this, though there are practically good strategies for selecting them. To approach the mentioned algorithm, we have to consider certain phases in the arrangement of the given witness set. This works similarly as with the guards. So first we compute the visibility polygon for each witness point, and the overlapping edges of these polygons creates then an arrangement that divides the polygon into disjoint faces. The key observation is now that only certain of these faces are actually important for our optimization problem AGPW. Firstly, we observe that for each face we can identify all witness points that can actually see the whole face. A face that is locally maximal within its neighborhood, that is a face that can be seen by more witnesses than all its neighboring faces, is called a light face. Note that two such faces are neighbors if they share at least one edge. If they only share a vertex, then they are not considered as neighbors. Mathematically, one would define here a partial order on the faces and would say that the face Fj is larger than the face Fi if the set of witnesses that see Fi is a subset of the set of witnesses that see Fj. A light face is then simply a face that is maximal with respect to this partial order. To make things clear here, let us consider another example. First of all, we create the visibility polygon for each witness point to obtain the arrangement. Into each face of the arrangement, we insert now the witnesses that can fully observe that face. The light faces are then simply those faces whose neighboring faces can be seen by a proper subset of the witnesses that can see the light face. Now what I noticed here is that it really comes down to how many witnesses can see each face. So you can write into each face the number of witnesses that can fully see that face, and the light faces are then exactly those with the locally maximal number in their neighborhood. I think this is much easier to remember. To understand now the purpose of these light faces, we have to take a look into the mentioned paper. You find there a theorem that states that if W is a finite subset of P, then there exists an optimal solution of AGPW in which every guard belongs to a light face of the arrangement of W. This does not mean, of course, that every solution must place guards in the light faces. It simply states that there always exists such a solution. The proof is actually not very difficult. This theorem has a significant impact on solving the art gallery problem with witnesses. In general, the optimization problem AGPW would require covering all witness points while considering all infinitely many possible guard positions in the polygon, which is practically unsolvable. However, thanks to this theorem, we can restrict ourselves to possible guard positions in the light faces of the arrangements defined by the witnesses. But since there are still infinitely many possible positions within these faces, one might think that this does not really offer an improvement. The key observation is now that the light faces are always convex faces. Moreover, a guard placed strictly inside such a light face can see exactly the same witnesses as a guard placed at one of the vertices of the face. Therefore, it is sufficient to simply consider the finitely many vertices of the light faces as possible guard positions. And now we really have something to work with. The issue with the AGPW optimization problem was that it contained infinitely many variables, and therefore an objective function represented by an infinitely long sum. The theorem from the paper allows us now to reduce the potential guard placements to only the vertices of the light faces from the arrangement created by the witness set. Therefore, the whole problem breaks down into a set cover problem. All this leads to a simple algorithm which can also be modified to finally solve the art gallery problem. First of all, let us formulate an algorithm to solve AGPW. Such an algorithm gets obviously the polygon P and the witness set W as input. The output, as you hopefully remember, is a minimal guard set G subset of P that covers W, but probably not the whole polygon. Regarding this, it is important to select good witness points, especially for the algorithm later. So what is a good witness selection? Well, there are actually 3 choices that are often used in the literature. One common choice is to place the witnesses at the vertices of the polygon. This is very straightforward since the polygon is already defined by its vertices and no extra computation is needed. A slightly better option is to place the witnesses only on the convex vertices of the polygon. This usually results in a less complicated arrangement as the witness set will contain fewer points than when using all vertices. Now if you really want to get the best out of your algorithm, you should use so-called Chva points, named after the mathematician Kyung-Yong Chva. According to the paper, the usage of these points resulted in the best practical performance. And the idea behind their construction is very simple. On the one hand, you take all midpoints between pairs of reflex vertices. And on the other hand, whenever you have an edge connecting a convex and a reflex vertex, you simply take the convex vertex of that edge. Once our set of witnesses has been chosen, we compute the resulting arrangement. In this arrangement we need to search for the locally maximal faces, so faces with a locally maximal containment number. Once this has been done, we extract the vertices of these light faces and store them in G fixed, because these are now the fixed potential guard positions. A minimal guard set G that covers W can then be obtained by solving AGPW using G fixed. As we already know, this can be formulated in a more compact way for a solver. The corresponding matrix A here has obviously a row for every witness and a column for every guard. The reason for this is that the universe consists here of the witnesses, and these are the elements that have to be covered. And the sets are basically the sets of witnesses that are contained in the visibility polygons of the guards. Therefore we insert a 1 into every row of this matrix if the corresponding witness is contained in the visibility polygon of the guard associated with that column. And doing this for every column yields the following matrix. By solving now this optimization problem, we obtain a solution vector x, which tells us which guards from the possible guard positions are chosen in the solution. And yes, these guards are then obviously returned by the algorithm. As you see, not the whole polygon has been covered, which is no surprise since we aimed to cover only the witness points. But in this case there is just one uncovered region in the polygon. The idea now is to place a new witness point into this uncovered region and hopefully achieve coverage of the whole polygon after applying the AGPW algorithm once again with the new witness point. Specifically in this example, the addition of the new witness point has no influence on the light faces in the arrangement of W. Because of this, the number of columns of our matrix does not change. But what will always change with additional new witness points is of course the number of rows of the matrix. As we store the elements of our universe in the rows, a new row must be added for each new witness point. Surprisingly, the solution with the one additional witness point covers now the entire polygon. Now let us compress this formally into an algorithm. The input is obviously the same as for the AGPW algorithm. The output is now a minimal guard set that covers the entire polygon P. Well, in fact, this is our goal, but in practice it is possible that the solutions might not significantly improve after some iterations. In that case, one would have to terminate the algorithm in a real implementation. While true, we simply repeat now exactly what we did in the AGPW algorithm, and we stop the algorithm as soon as our guard set G fully covers P by simply returning G. If this is not the case, then there are uncovered regions inside the polygon. In that case, we pick one random point from each uncovered region, collect all these points in the set U, and then enlarge W by adding the points from U. Now let me summarize. Before the algorithm starts, we have to compute all convex and reflex vertices of the polygon to determine the Chva witness points. These witness points create then an arrangement in the polygon. Once the arrangement is complete, we In this arrangement we compute the containment number for each face and identify all light faces. Then we extract all vertices of the light faces to model the associated set-cover instance, which we solve with an appropriate solver. Typically this yields a solution that covers all witness points, but not necessarily all points in the polygon. Therefore we identify all uncovered regions, place exactly one witness point in each of those, and repeat this process until the solution fully covers the entire polygon. Remember that the solution of AGPW is always a lower bound of the original art gallery problem, since it needs to cover only finitely many points. Therefore this algorithm is in some sense an algorithm that potentially increases the lower bound from iteration to iteration. Because of this, it's clear that once the algorithm returns a solution that actually covers the entire polygon, we can be sure that it uses the minimal number of guards to achieve this. Note that there is actually a way to improve this algorithm by also computing an upper bound for the art gallery problem in every iteration of the while loop. This is really not difficult, but since the video is already long enough, I will not cover it here. However, feel free to take a look into the paper for more details. And by the way, be careful when computing a point in every uncovered region. It is not a good idea to always select the centroids of the uncovered polygonal faces as the new witness points. The centroid is obviously not always inside the face itself. Consider for instance a polygon like this. So what can you do instead in situations like this to get one point from this polygon? Well, we can use for instance the ear clipping algorithm to triangulate the uncovered face, and then we simply pick the centroid of any random triangle from this triangulation. Using this approach you can always find a point that lies inside the uncovered region.